I'm Elizabeth Angel. I'm EERI's Communications and Program Manager, and I'd like to welcome you on behalf of the Earthquake Engineering Research Institute. We're the leading nonprofit organization working to connect professionals from a wide range of disciplines who are dedicated to advancing earthquake resilience in the United States and around the world. And our members include researchers and practitioners from a wide range of fields who share this goal. And we're excited to be presenting this webinar to you today. I'll turn it over now to Volkan Sevilgan, who's the president of the Northern California chapter.
Hi, everyone. I would like to welcome all of you to our presentation. We are doing this presentation on behalf of our Northern California chapter and also part of the Learning from Earthquakes program of the Earthquake Engineering Research Institute. Our chapter is dedicated to reduce earthquake risks in Northern California, and we have about 200 members. Our membership ranges from seismologists to earthquake engineers to social scientists to policymakers, and we would like to welcome all of you to join our chapter. We have two great speakers today, Hiroyuki Goto and Keita Uemura, and they'll be talking about the recent earthquakes in Japan. And for introduction for the speakers, I would like to hand the virtual microphone to Bruce Mason. Thank you.
Thank you very much, Volkan. I would like to welcome everyone to the briefing on the magnitude 7.4 earthquake that struck offshore Japan on March 16th. On March 16th of this year, a magnitude 7.4 earthquake struck offshore Japan. The epicenter was in the same general area as the Great Tohoku earthquake of 2011. Two speakers are joining us from Japan. The first will deal with the strong motions that this earthquake generated onshore Japan. A 1.2 G peak ground acceleration was recorded. And considering the hypocenter was about 40 miles deep, this is somewhat remarkable. He will talk more about this and other aspects of the strong motions recorded from this event. Our second speaker will deal with damage to the Shinkansen bullet train. One train was derailed and there was significant damage to many of the facilities of that particular line. Rapid repairs were enacted and the train was back in service 6 weeks after the event. So our second speaker will talk about that. Now, each of our speakers today will talk for about 20 minutes each, and we'll have the remaining time will be for a question and answer period. Our total program time will be about 60 minutes today. We encourage questions from the audience, and how you will do that is you will hit the Q&A button you see on the bottom of your screen, type in your question, then behind the scenes, Volkan will compile your questions. He will come back later in our program and he will pose the questions to our speakers. Now, we recognize that we might have more questions than we have time. So both of our speakers today have kindly provided their email addresses, and you see them on the screen here. So you can send them questions directly, and they will try over the coming days to answer your questions. Now what I'd like to do is introduce our first speaker, Dr. Hiroyuki Goto. He's with the Disaster Prevention Research Institute of Kyoto University. Dr. Hiroyuki, could you please proceed?
Thank you very much, Bruce. So I would like to talk about the strong motion of the last Fukushima earthquake in March 2022. So this is Hiroyuki Goto. I am belonging to the Disaster Prevention Research Institute of Kyoto University. So I'd like to start my presentation of the introduction of what the earthquake of the last Fukushima earthquake. The Fukushima earthquake in the 2022 is occurred in the offshore of the Tohoku areas. The magnitude is about 75 7.4 in local magnitude scale, and also the moment of magnitude scale in 7.3. The depth of the earthquake is 57 kilometers. This earthquake measures the maximum intensity in JM scale is about 6 plus. That is not the maximum value of the seismic intensity scale in JMA, but that's observing very large shaking in the areas of the Tohoku areas. This earthquake caused several important infrastructure damages, especially in the flight terrain that was presented in the later by Keita Uemura. But I will explain some about the another minor damages. Is about 3 fatalities of this related earthquake damage, and also 20,000 damaged houses was recorded. And one thermal power station that was Sinch station is still out of service due to these earthquake damages. This earthquake is occurred in the offshore region of the Tohoku areas, but this area of recorded the very large earthquake in 2011 that was so-called Tohoku earthquake. The Tohoku earthquake occurred in the interplate earthquake between the Pacific plate and inland the North American plate. But this earthquake occurred inside of the ocean plate that was so-called interslab earthquake. This is recognized by the distribution of the aftershock of these main shocks. The Japan Meteorological Agency found it out the aftershock distribution aligned to the eastern dipping fault plane. Therefore, we can recognize this earthquake is the reverse fault type mechanism, and also this aftershock and fault plane eroding in the north-south directions. That was almost coincide with the direction of the fault plane of the last 2011 Tohoku earthquake, but the earthquake type and mechanism is very different from the last one. But this kind of the intraslab earthquake is not minor in this region. The major interslab earthquake record observed in the last year in the February 2021. That was almost similar rotation of the hypocenter. For example, in this earthquake, the hypocenter located in the marked in the star in this map, and aftershock distribution aligned in the northern part of this hypocenter. But the last earthquake in the 2021, the hypocenter located an almost similar rotation and in the area of the race earthquakes, but the aftershock distributed in the other side of the fault plane. This indicates that this earthquake 2022 and the last earthquake 2021 is very similar mechanism of the interslab earthquake, but the fault is very different. This earthquake in 2022 ruptured toward northeast direction, but 2020 event ruptured toward southwest direction. That was quite different of the different characteristic in between the 2021 and 2022. Also, several different earthquake type of the interslab earthquake were recorded in this region. The observed peak run acceleration is very important issue that was already mentioned by Bruce in the introduction. The 2 stations in the Miyagi Prefecture observing exceeding 1 gravitational acceleration observed at these stations. The largest record was observed in the MYG 807 in the Kikunet station. That was almost 1,100 Gauss. And also MYG 810 also observing almost equivalent to the one gravitational acceleration, that with the horizontal component. And also large peak ground acceleration distribution in the Pacific coast of the area of the Tohoku areas. That was very comparable to the direction of the fourth parallel directions. Also, the peak ground velocity is almost exceeding 70 centimeters per second, observing at Miyagi H10 and also FKS Zoma stations. The large peak ground velocities observing around the Miyagi and Fukushima prefectures. But the important one observing in this peak ground velocities is also the large peak ground velocities distributed along the coastlines, north to south in the areas of the Tohoku areas. To compare with this majority or the minority of these earthquake records, the peak ground acceleration is compared to the very famous ground motion models. The red points indicate the peak ground acceleration compared to the distance, fall to distance from these models. And also blue point is the peak ground velocities. The Miyagi H07 that was observing exceeding 1.0 gravitational acceleration, that was a little higher than the mu plus 1 sigma line of the past earthquake records. And also, but the majority of the data almost follow these past ground motion models. And also velocity peak ground velocity followed by the ground motion model. This suggests the earthquake records of this 2022 event is not a strange earthquake, but some of the stations observing a little typical record, for example, exceeding 1.0 gravity acceleration at this station. Therefore, we need to identify the reason, for example, to compare with the last 2021 earthquakes. Remind back to the last earthquake for almost the same trend seen in the peak ground acceleration records. But also the Miyagi H10 observing the large peak ground acceleration exceeds the 1.0 gravitational acceleration. This means this earthquake and these types of earthquake, for example, in the interest of earthquake and the depth and the hypocenter location, tends to enhance the high frequency radiation and high frequency components of the peak ground acceleration. And also another reason to reach this kind of very large earthquakes, very large peak ground acceleration, is the local sites or local station responses inducing high frequency components. That was not exactly identified at this moment, but I can say some of the example in the past literature. If you are interested, please look at this literature. Anyway, I will look into the detail about the peak, the velocity waveforms. So I pick up 3 station records in the diagram. You can see these velocity waveforms. The ground shaking continues about 20 seconds along the Pacific coast. And also, you can see the obvious, the 2 wave packets in the records. For example, you can see in the FKS 001 station records, and also you can see somewhat the Miyagi 010 stations. I think this is not a doublet at the same location. This is because of the source rupture process. Say, for example, this fault rupture includes the two significant asperities or large slip areas involved in the rupture process. I think this is because of these two parties observing in the records. I compared the acceleration response spectra in the typical records in the stations. This diagram shows the acceleration response spectra. The spectral shapes, these red and blue and black lines, are quite different in the size. The MRGH10 response spectra enhance very high frequency components, but MRG010 stations enhancing about around 1 to 2 periods of the components. That divergence is very important characteristic of these earthquakes. But I wanted to notice you about the every spectrum. I brought together the JMA Kobe acceleration response spectra in this diagram. You can see the major frequency range, for example, 0.5 to 2 seconds. Then you can the earthquake response spectrum do not exceed the JMA Kobe response spectrum. Therefore, the earthquake ground motion is very huge, but that is not significantly large comparable to the JMA Kobe earthquakes. And also, this record compared to the acceleration response spectra is the last 2021 earthquake. The solid line indicates this earthquake response spectrum, and dot line indicates the last 2021 earthquake record. The FCS-01 is almost similar shape on the last and this earthquakes, and also MRGH10 also is very comparable to the almost same spectral shape compared to the last 2021 record. This means the spectrum shape is controlled by the source rotation and also the depth, and also the including some local site effect involved in and forming this frequency content of the size response spectrum. Therefore, I cannot summarize all of the reasons to differ the spectral shape, but I think the main reason of the difference of the spectral shape is due to the difference of the site response of these three stations. Therefore, we need to see the site response of the station to account for, to discuss about the strong ground motions in the region of this earthquake. That is very important to discuss the site response in these earthquakes. So, as we know that this area is damaged due to the last 2011 Tohoku earthquakes, we needed to compare this earthquake ground motion of 2022 earthquake is significant, or the 2011 earthquake is more significant. To clarify these differences, the differences of the ground motion levels, I calculate and I categorize the largest record since 2011, including the 2011 Tohoku earthquake, the largest echoes in each site. This gray dot means the largest ground motion records is occupied by the last 2011 earthquakes. But colored sites is occupied by the largest records by the same colored stars of the hypocenter event. This red star indicates this 2022 earthquakes. You can see this red dot appear in this area. That means this area is larger than the 2011 earthquake records. Therefore, some of the infrastructure facilities or some house damages caused by that was not damage due to the 2011 Tohoku earthquake, but this earthquake caused the damage that was very usual because of this earthquake observing larger than the 2011 earthquake. When we compare to this acceleration response spectrum, the red line indicates this earthquake response spectrum, and black line indicates 2011 Tohoku earthquake. The spectrum shape is very similar, but you can see the significant period component to the infrastructure, 0.5 to 2 seconds. The red line is a little larger than the previous earthquake. Therefore, some infrastructure is damaged due to these earthquakes. For example, in this FKS 007 is located very close to the site, the Tohoku Shinkansen bullet trains. Therefore, some infrastructure damages may be caused due to the differences of the last earthquakes. But I noticed about these levels of the earthquake response spectrum that was quite less than the JMA Covell acceleration response. This means if we satisfactorily make the involve the seismic design in considering the past large earthquakes, that can be damage can be reduced due to these earthquake records because the magnitude of the earthquake response spectrum is very small. Okay, let me summarize my presentation. The earthquake, in the section of the earthquake, Fukushima earthquake in 2022 was an inter-server event, which is similar focal solution with the last 2021 event. This earthquake 2022 ruptured towards the north, resulting large ground motion observed at the northern part of the Miyagi Prefecture. The ground motion section, I introduced the differ in the frequency contents in the site. That was maybe explained by the local site conditions. But I noticed about this, the frequency contents of the acceleration response does not exceed the JMA Covell records. Compared to the 2021 records, responses in 0.5 to 1 second are enhanced. In the northern part of the Fukushima, the ground motions of this earthquake exceeded that of the Tohoku earthquake in 2011 and was the largest since 2011. That is the main reason some infrastructure and houses were damaged that was not damaged in the 2011 earthquakes. Thank you for your kind attention. Thank you very much.
Thank you very much for a very informative presentation. You presented quite a bit of material, so I'm glad that we are recording this so future people can be able to review it. I'm sure we'll have many questions on this. I would like to introduce our next speaker. Our next speaker, Dr. Kita-san, will talk about damage to the bullet train system. Could you please proceed?
Thank you, Mr. Bruce, for your introduction. I'm Keita Uemura from Kyoto University. Today, I'd like to talk about the damage to railway facility of the Tohoku Shinkansen line in Fukushima earthquake. And as Professor Goto mentioned earlier, a magnitude 7.4 earthquake occurs of the coast of the Fukushima Prefecture on March 60th. And this figure is taken from the Professor Goto's report. The Tohoku Shinkansen Railway is located as shown here, and the Shinkansen bullet train derailments and the structural damage to pier viaducts occurred in this earthquake. So in my presentation, I'll describe the Shinkansen bullet train derailments and the structural damage to piers and viaducts. However, my research is focused on the railway facility, especially the structure such as the pier and the viaduct. So I'll explain the damage to piers and the viaduct in more detail than the Shinkansen bullet train derailment. Now, first of all, I'll explain the Shinkansen bullet train derailment. In this earthquake, the Shinkansen bullet train had 60 of the 17 car train derailed, and the maximum derailment of the vehicle was approximately 1,000 millimeters. And near the derailment point, and two seismometers were placed, and the observed PGA was 5.83 and 8.11 meter per second squared. So, and although the large acceleration was observed, but no one was killed or seriously injured due to the derailment, fortunately. And this is due to the fact that the anti-derailling gird worked effectively in this earthquake. By installing the anti-derailling gird, even if the vehicle derailed, the L-shaped gird hit the rail and prevent the wheel from deviating too far. So in this earthquake, the anti-derailling gird was on the rails in the 50 of the 60 derailed axles. So thus it is considered that the anti-derailling girds worked effectively. However, the detail and the cause of the derailment of the Shinkansen bullet train are under investigation. So I don't have more information. I'm sorry. And incidentally, after this earthquake, it took 2 months for the Shinkansen bullet train service to return to regular. And the service was suspended in some sections from the 60 March to the 40 April. Then after 40th April, the service resumed with the temporary schedule, and the Shinkansen bullet train ran slowly in some sections. Finally, the service resumed in all sections with a regular schedule on the 30th May. So the interruption of the service was most likely due to the severe structural damage to the piers and viaduct. So I'll explain the structural damage to pier and viaduct in this earthquake. First of all, I would like to give a brief overview of its history of the earthquake damage. Since its construction, the Tohoku Shinkansen line has experienced several strong earthquakes, causing the damage to facility and the structure. For example, the 1978 a magnitude 7.4 earthquake occurred off the coast of the Miyagi Prefecture. At the time, the Tohoku Shinkansen line was under construction and suffered much structural damage. Also, as you know, the magnitude 9.0 magnitude of the Pacific coast of Tohoku earthquake occurred in 2011. Since then, there have been several earthquakes exceed magnitude 7.0, which were considered to be the aftershock of the Great Tohoku earthquake in 2011. Therefore, it is necessary to understand the history of the repair and retrofitting for past earthquake when investigating the damage caused by this 2022 earthquake. So, under such circumstances, last year, an earthquake occurred in Fukushima Prefecture, which is considered to be the aftershock of the 2011 of the Pacific coast of Tohoku earthquake. In this earthquake, only the failure of the two-story RC frame viaduct were confirmed, and significant damage to the column was not observed, and only the failure of the middle beams of the viaduct were confirmed. Generally, in the two-story RC frame viaduct, the failure of the middle beam occurred first absorbing seismic energy and reducing column damage. Therefore, the fact that the damage occurred only the middle beams of the two-story RC frame viaduct can be considered as a positive indication that the behavior of the viaduct was following the design concept. However, I think there is the influence of the past repair for the RC structure. In the 2011 off the Pacific coast of the Tohoku earthquake, shear cracks on the middle beams of the two-story RC frame viaduct were observed. And subsequently, the middle beams were repaired by the injecting mortar into the cracks. And then in 2021 Fukushima Prefecture earthquake, the shear crack reappeared along the repair screws on the middle beams. Therefore, there may be issue with the decrease of the structural seismic performance that have been repaired in the past. With the background of the damage history and the current situation of the Tohoku Shinkansen structure, I would like to explain the damage to the structure caused by this 2022 Fukushima Prefecture. This earthquake caused structural damage to the middle beams of the two-story RC frame viaduct and the column structure over the wide area. And I will describe the significant structural damage in this earthquake. First, I'll explain the damage to the middle beams of the two-story RC frame viaducts. First of all, I describe the structural damage in the central area of the Fukushima Prefecture. In this area, only the middle beams of the two-story RC frame viaduct were found to be damaged, and the damage to the column was not observed. This can be positively considered as the behavior in the accordance with the design concept of the damage control, where the middle beams are damaged and the damage to the column is mitigated. On the other hand, the following problem can be considered, I think. The damage occurred only on the middle beams with repair skirts. Considering that the damage was not observed in the middle beams without the repair skirts, it is possible that the middle beams with repair skirts in past earthquake was easy to damage. And the damage to the viaduct was also observed in the area where the Shinkansen bullet train derailment occurred in Miyagi Prefecture. The damage in this area was more severe than in the area shown in the previous slide. The concrete sparring and the exposed level were observed on the middle beams, and the damage occurred along the past repair skirts. So it is possible that the seismic performance of the repaired beams is not adequately maintained, and the middle beams damage occur easily. Also, these photos show that this structure has been damaged and repaired several times. Looking at the damage to this structure, the cracks were observed in the 2011 Great Tohoku earthquake, and the beam was subsequently repaired by mortar injection into the cracks. And then in the 2021 Fukushima earthquake, the middle beam cracked again and was repaired by injecting mortar into the cracks again. And finally, in this 2022 earthquake, cracks along the repair skirts were found. So it is noted that there are very few studies on whether seismic performance can be maintained when the structural member have been damaged and repaired multiple times. So we must investigate whether the structural member repaired multiple times have the required seismic performance. There is a summary of the damage to the middle beams of the viaduct in this earthquake. Similar to last year's earthquake, damage to the viaduct's middle beams occurred over the wide area. And the concrete sparring and exposed level are observed on the middle beams. And in addition, the damage initiating from the repair skills caused by the past earthquake was remarkable. And therefore, there are issues regarding the seismic performance of the member after the multiple repetition of the damage and the repaired. Next, I'll describe the damage to the column structures. First of all, I will explain the damage confirmed in the northern area of the Fukushima Prefecture. This structure suffered the most severe damage in this earthquake. As you can see, the base of the columns were covered with the blue sheets, so this photo does not show the detail of the damage. However, you can see that the column have settled and the entire viaduct is tilted. And these are the detail of the damage to this viaduct. This picture from the East Japan Railway Company report and the Twitter of the resident. As you can see, the column has lost actual load support capacity, and the column have the settled. And the diagonal shear cracks on the column caused significant damage to the core concrete. And in this photo, the sparring of the concrete in the diagonal direction can be seen, and the hoop reinforcement was significantly plasticized. So it can be judged that the shear failure of the columns occurred in this viaduct. Then I describe some important aspect of the damage to these structures. The upper columns of this viaduct were retrofitted by the steel plate jacketing. So it means that the seismic performance of the structure was evaluated, and it was judged that the lower column did not require seismic retrofitting. However, in this earthquake, the shear failure occurred at the column. So it was possible that the seismic evaluation for this viaduct were not correct, or the seismic retrofitting of the upper columns resulting in the structural weakness being shifted to the lower columns. So there are issues regarding the decision to the seismically retrofit the structures and the judgment of the seismic performance of the entire structure after the retrofitting of some components. And damage was also observed in the column near the Shinkansen bullet train derailment area. And in the case of the columns, the buckling of longitudinal burrs at the base of the columns occurred, and it can be conducted that the flexural failure of the occurred. Therefore, unlike the shear failure columns introduced in the earlier slide, this failure mode was ideal. And on the other hand, it is important to consider the whether seismic wave, whether the ground motion was large enough to allow the occurrence of the failure of the columns. And in this area, the neighboring the column had been seismically retrofitted. No damage was observed in this structure with seismic retrofitting. It is clear that the seismic retrofitting functioned effectively. On the other hand, it is necessary to examine the whether seismic retrofitting of the flexural failure columns is necessary or not. And moreover, there is a structural similarity between the shear failure viaduct and the flexural failure viaduct. Both columns was supporting the large girder, as you can see. it is possible that the weight of the girder was so large that the large inertial force caused the column to fail. So it is necessary to examine the relationship between the extent of the structural damage and the magnitude of the ground motion in detail. Also, in other areas, the longitudinal was backed and the concrete spalled. Such failure was observed in the broad area. On the other hand, the damage to seismic retrofitted column was not observed. For example, in these columns, the neighboring column had been seismically retrofitted, and the damage was not observed in those columns. The fact that the damage occurred only to the non-retrofitted column is common with the damage in other areas. These are summary of the damage to the column of the Tohoku Shinkansen structure in this earthquake. Shear failure of the columns occurred in the RC viaduct. So there is an issue regarding the decision to the seismically retrofitted to the structure and the judgments of the seismic performance of the entire structure with some retrofitted components. And the damage occurred only the non-retrofitted column, while the neighboring retrofitted column was not observed. Thus, it was necessary to investigate whether seismic retrofitting to the damaged column was needed or not. That's all. Thank you for your listening.
Thank you. Thank you very much for a very informative presentation. You presented a lot of information. Will take some time for me to digest. I want to compliment both of our presenters today for their graphics, for they had converted their slides to English so that we can be able to read them and interpret them quite easily. So I would like to thank them again for their visual slides that they presented. Now what I would like to do is turn control of the meeting over to Volkan so he can pose questions to the speakers. Volkan, can you please proceed?
Thank you, Bruce. Thank you, Keita. Thank you, Hiroyuki. Amazing presentations. My first question to Hiroyuki, perhaps you can share your screen again regarding to comparison of the 2022 March earthquake versus February 2021 earthquake and Tohoku earthquake and Kobe earthquake, the acceleration differences. One thing that really, that was the spectral acceleration differences. One thing that you have shown us, which is really remarkable, that magnitude 7.4 earthquake created larger acceleration than the Tohoku earthquake. And with the Keita's presentation, we are actually seeing a lot of damages from that earthquake compared to Tohoku. So both observational acceleration and also resulting damage seems consistent. Let's go to that graphic. That one y-axis, I think, was the spectral acceleration. The x-axis was the period. So the red line, I don't want to give you a presentation, but in the middle panel, the red line is the magnitude 7.4 that occurred most recently. And the black line is the Tohoku earthquake.
Yes, and magnitude 9.0.
Correct, 9.0 Tohoku earthquake.
Yeah.
And what we are basically seeing for all the frequencies or period that really matters for structural damage, this 7.4 was much higher for Fukushima region.
Yes, right.
How about the other region?
Yes, right. Of course, this panel shows the typical example of this indication of the red sites indicated in this map here, right? Do you see my cursor?
Yes.
So, of course, the other location, for example, in the northern part of the Miyagi Prefecture, that is occupied by the largest ground motion by the 2011 earthquakes.
Okay.
The gray location is the largest ground motion is by the 2011 earthquakes. But this led, for example, 6 sites are exceeding the 2011 earthquake.
Wonderful. I also have another important question comparing 2021 and 2022.
Mm-hmm.
So let's take a look at that. 2021 versus 2022. And
Mm-hmm.
there we are seeing 2021 is much lower than the 2022 earthquake. Was that rupture propagating towards land versus maybe this rupture directivity related, I'm assuming.
Yeah. That's true. I compare with the differences of these earthquakes. So, for example, as you mentioned in the questions, this earthquake ruptured towards to the north, and the last 2021 earthquake ruptured towards south. The difference of the spectrum of the ground motion, I compare with these 2 earthquakes. This red indicates the larger spectral amplitude compared to the 2021 earthquakes. This means the northern part of the Tohoku area is much higher than the southern part. That means that this 2022 earthquake enhanced compared to the last earthquakes. That is not exactly clear the reason, but of course the one possible reason is the forward directivity towards the north rupturing. And also, of course, the distance is different. For example, this region is very close to the fault plane itself. Therefore, that is a little different to the last earthquake.
Are they both dipping towards northwest?
Yes, that is the same, exactly the same. The north
dip direction is the same. So the red dots are where the rupture is essentially, right?
Yeah.
And that's 2022, and the other one is 2021. So it's slightly closer to the land. So that's probably one of the reasons why.
Yes, right.
But what was the argument about the rupture direction? Are they both rupturing more or less the same way?
Yeah, I'm not sure how we cannot clarify that divided by 2 effect in the difference of the distance and also the effect of the forward directivity, but we need to discuss more about the analyze this.
One part that I missed. Were they rupturing the same way in both cases?
No, different.
Different.
This stutter, can you see that? This is very difficult.
Yes.
I'm sorry. This stutter is the hypocenter location, and this dot means the fault plane. That means the hypocenter start to rupturing this fault plane in this direction in this aspect.
Oh, I see.
Yes, this is a different direction. Must be.
So that's very interesting because it's 2022 earthquake actually ruptures away from the land. The other one ruptures towards the land, which you would expect. Rupturing towards the land would create larger directivity effect. But you don't see that in the data. Let me ask you this. If you look at the stations to the south towards the ruptured direction, I bet you would see a different picture there.
Yeah, I think that is very simply answered because of this slide. That is the same map as I explained in the categorized. In the blue star means the 2021 earthquakes. Can you see the blue dot in the south areas? That means this area is the largest earthquake, including the 2022 earthquakes. That is the largest record observing in this area. That was maybe related to the forward activity of the last event, I think.
I see. This makes a lot of sense. Okay, so the intuition is correct in that way. So this is amazing. Thank you so much for this. And I have a question for Kato-san. Also, surprisingly, the damage to Shinkansen looks like it's been the operation was hampered by a month, completely hampered, and then another month with maybe like a low level speed. So it's 2 months interruption in that structure. So that's incredible. So one important thing that I saw that you had a beautiful tree earthquake comparison figure in the showing. Maybe you can share your screen as well. So you are showing damages from 3 earthquakes, 2021, 2022, and then the Tohoku. And if you cover the title, I bet nobody would guess which earthquake is which in terms of damages. Everybody would go for the 2022 earthquake as being the Tohoku damage. If you look at the
and the in the area where the Shinkansen bullet train derailment occurred, or the shear failure of the column was confirmed, the damage to the structure were larger than that caused by the Great Tohoku earthquake in the 2011. And I would like to talk about the relationship between the spectrum and the structural damage. Okay.
Yeah.
And just a moment. To relate to the previous question to the Professor Goto, these are the relationship between the structural damage and the acceleration response spectrum. And the orange line represented the acceleration response spectrum of the observed seismic wave in the 2022 earthquake. But it noted that these spectrum were not in vicinity of the damaged structure, but somewhat near points of the damaged structure. The spectrum observed in this earthquake was larger than the current design spectrum, the L1, that allows the structure to be damaged, represented yellow line, but smaller than the current design wave, seismic wave spectrum L2, that doesn't allow the structure to reach the ultimate state, such as the buckling of longitudinal bars or the spanning concrete significantly. So anyway, these figure shows that these seismic waves, the ground motion observed in this earthquake, were somewhat large for the railway road structure, but it is investigated whether the such damage were allowed to occur or not.
So what we are basically seeing is larger than 1.5 G shaking for low frequencies, right? That was the frequency. Yeah.
And the many electric pole and the rail was damaged in the broad area. So those damage caused the suspended of the Shinkansen bullet train service for a month after the earthquake, I think.
How about damages to the tunnels? Do you have any observations for that? Or any damage in tunnels?
I think the no significant damage to the tunnel was observed.
Most of the bridges and viaducts and structures like that. Another thing that you have also shown that one of these steel sheeting, I think, or jacketing, that for the retrofitting the structures, potentially transfer the damage to the bottom section instead of perhaps it could be a little bit more flexible in the upper part of the columns, but it's so stiff now, it potentially increased that thing. Did you see any area that has a similar structure, one with retrofit and one without retrofit? And I guess what I'm trying to get at is, can you show a case that how retrofit performed what would happen if the same structure exposed to the same shaking without retrofitting? And what happened with that kind of retrofit?
In the many area, the retrofitted column and the non-retrofitted column is very near the neighboring. But in all cases, the retrofitted column is not damaged, but the neighboring non-retrofitted column was damaged. But on the other hand, the retrofitted column was not damaged in all cases.
Okay, so let me ask you another thing. Isn't this steel jacketing? Is it possible that there's damage inside that you are not seeing?
Yeah, you're correct. And
Could be, right?
Yes.
Yes.
So in order to check the damage against the earthquake, the RB retrofitted is conducted. Okay, this retrofitting enhances the shear strength of the structural member, and we can see the damage at the time of the earthquake occurred. So yes, so this method of the seismic retrofitting of the structural member were conducted in broad area in the Tohoku area.
In other words, if there were damage, you would be able to see it because you are able to remove the metal jacketing to see if there's damage. Okay, perfect. That actually answers the question. I would like to ask Bruce to continue a few questions.
Well, okay. Thank you very much. I may have one question. We're drawing to the close of our time, but this would be to Dr. Kita. The damage to the columns and beams that you've described, is this an acceptable response? In other words, are you considering changing your design criteria? Because again, your structure was damaged 10 years ago, repaired. 10 years, we have another earthquake. Again, we see similar damage. It seems to me for such a key system as your bullet train that this would be something you would want to circumvent going forward. So has your design criteria increased as a result of these observations?
Yes, and most of the damaged structure was built in the 1970s. So compared with the date of the construction of the damaged structure and today, there are many change points on the seismic design. So, but in all the case, in the middle beams was repaired. So I think it's necessary to the retrofitting, the seismic retrofitting to the middle beams instead of the repair. So then I can't understand the relationship between the damage to the viaduct and the Shinkansen bullet train derailment. But there are somewhat effect of the damage to the viaduct to the derailment of the Shinkansen bullet train.
Okay, very good.
Estimated.
Okay, very good. Thank you very much. Our time is drawing to a close. I would like to thank both of our presenters for taking the time today to go through a very thorough presentation of the two subject matters. I thank you again. I'd like to turn control over to Vulcan for some closing remarks.
All right. Thank you, everyone. One last question. I'm not going to let you go before that is answered. Earthquake early warning and Shinkansen performance. Do you have any sense that whether or not that was effectively employed here, and so it's actually saved life? What is your opinion on that or observation?
And okay.
And it is very not direct answer maybe, but as I know, this earthquake is little the typical earthquake. This is because this earthquake occurred in the maybe 38 minutes. But before this earthquake occurring, another small earthquake occurred 2 minutes before.
Yes,
Therefore, the early earthquake warning alarms at the previous earthquakes. Therefore, we have 2 minutes reaction. For example, stopping the bullet train or any kind of the earthquake warning system. That is not a common situation, maybe. But
How long would it take for that train to stop, actually, or slow down to the safer?
It depends on the case, of course. But
it is enough time to stop for 2 minutes. So
2 minutes is enough.
I estimated that the Shinkansen bullet train was slowing down or stopping due to the earthquake early warning in the 2 minutes before the minor earthquake.
I think the question whether or not if that earthquake didn't occur 2 minutes before the 7.4, whether or not Shinkansen would have enough time to slow down to save people. That's basically. And do you have any sense of that?
Yeah. If we discuss about earthquake warning system of the effect of these earthquakes, we need to think about the time differences. Either 2 more minutes the reaction time. That's my question. That's my answer.
All right, thank you so much. This has been a fantastic presentation, and I'm sure a lot of us learned a lot. And that also shows the number of questions that we received and number of questions that I can come up with. I would like to thank all of the participants and the panelists on behalf of the Northern California chapter of Earthquake Engineering Research Institute. And here's for the closing remarks for Elizabeth.
Great. Thank you again so much for attending today. We'd like to ask you to complete a brief post-webinar survey, which should pop up as soon as the session ends. If you'd like to learn more about EERI, or better yet, join us, you can see our website here, and you can also find out about future webinars in the Pulse newsletter. Finally, I just wanted to thank both FEMA and also our members of EERI, like yourselves, for providing the support that allows us to make these events possible. Thank you, and look forward to seeing you at the next one.